Hello and welcome to this 13th Algorithm Selection and Development lecture in this course Master in Artificial Intelligence. So in this lecture we will talk about how to develop an iterate algorithm and in which how to use the techniques like regularization, dropout, now batch normalization and learning rate scheduling that can help you improve model generalization and performance. So as I was mentioning, this is what we will do in this use technique, learn how to use techniques like regularization, dropouts, batch normalization and learning rate scheduling in this lecture to improve model generalization and performance. So question is how to use these techniques to improve model generalization and performance. And these are the techniques that we talked about: regularization, dropouts, batch normalization, and learning rate scheduling. So let's take a look at each of these. So let's start with dropouts. So how to use dropout to improve model generalization and performance. And here, model generalization we mean is the ability of the model to work with in different scenarios and with different kind of data, right? So how to use dropouts? Any thoughts? What is dropouts and how to use dropouts to improve this model generalization and performance? See, dropout is a regularization technique commonly used in neural networks to improve the performance of the models, and it works by randomly dropping, which means setting to zero a fraction of the neurons during training, effectively creating a smaller and simpler network architecture. And how that happens, this is how you can use dropouts to improve model generalization and performance as we go forward in next couple of slides. So you need to begin by adding dropout layers. Insert dropout layers into the infra architecture of your neural network, typically after the activation function of activation functions of the hidden layers. Specify the dropout rate, which represent the fraction of neurons to drop during each training iteration. A common dropout rate is between 0.2 to 0.5, but the optimal value may vary depending on the specific problem and the data sets. Then you train the neural network with dropout enabled during the training phase, and during each training iteration, randomly set a fraction of neurons in the dropout layers to zero with probability equal to specified dropout rates. Now, this process effectively creates a different and simplified network architecture for each training iteration, preventing neurons from co-adapting and promoting more robust feature learning, right? Then you need to, during the testing or inference, disable dropout by setting the dropout rate to zero. This allows the model to use all neurons in the network, ensuring consistent and deterministic prediction. So test without dropouts is the next step. Then you regularize the model where you make the dropouts act out in the form of regularization by adding noise to the network and preventing overfitting. By dropping neurons during training, dropouts prevent the network from relying too heavily on the specific neurons or features, encouraging the network to learn more robust and generalizable representation. And then you experiment with dropout rates. You experiment with dropout rates, with different dropout rates to find the optimal balance between regularization and model performance. Start with the moderate dropout rate 0.2 and adjust it based on the performance on the validation set or through the cross validation. Dropout rates can be used in conjunction with other regularization techniques such as L1, L2 regularization to further improve model generalization. Experiment with different combinations of regularization techniques to find the best configuration for your specific problem. So combined with other regularization techniques. And finally, monitor the performance of the model during training and validation to ensure that dropout is effectively preventing overfitting without compromising model performance. Use techniques such as early stopping to prevent overfitting and achieve optimal performance. So by incorporating dropout in the training process of your neural network, you can effectively improve model generalization and performance, leading to better performance on unseen data and increased robustness to noise and variations in the input data. Then you need to, let's look at batch normalization. So how do you use batch normalization to improve the process? Now this batch normalization is technique used to improve generalization of the neural network by normalizing the activations of each layer. It works by standardizing inputs to layer before applying the activation function, and this effectively stabilizes the training process and accelerates convergence. So let's look at how to use this batch normalization process. So you start by inserting batch normalization layers into the architecture of your neural network, typically after the linear transformation when you are fully connected or convolutional, and before the activation function of each layer. Batch normalization layers normalize the activation of each layer by subtracting the batch mean and dividing them by the batch standard deviation. Then you train the neural network with batch normalization enabled during the training phase. During each training iteration, calculate the batch mean and standard deviation of each layer activation using the current batch of the training data. Normalize the activations of each layer using the batch mean and standard deviation, and then apply the activation function. The normalization process helps stabilize the training process by reducing internal covariate shift and accelerating convergence. This accelerates convergence. Then you test without batch normalization during testing and inference. Disable the batch normalization by using the population statistics, the running mean and the standard deviation instead of the batch statistics. You calculate the population mean and standard deviation of each layer's activation using the moving average of the batch statistics collected during training. Normalize the activation of each layer using the population mean and standard deviation, and then apply the activation function. This ensures consistent and deterministic prediction during testing, as batch normalization is not needed for single examples. Then what you do is you regularize the model. Uh, Batch normalization acts in the form of regularization by reducing internal covariate shift and preventing the network from becoming too sensitive to small changes in the input distribution. And by normalizing the activation of each layer, batch normalization helps stabilize training process and improve the generalization of the model. Then you experiment with hyperparameters of the batch normalization, such as momentum parameter for updating the running statistics and epsilon parameter, the numerical stability. Adjust the momentum parameter to control the rate at which the running statistics updated during training. Tune the epsilon parameter to prevent numerical instability when dividing by small value. Then you combine with other regularization technique, like we saw with the dropout regularization. This can be used in conjunction. So use in conjunction with other regularization techniques such as dropout to further improve model generalization. Experiment with different combinations of regularization techniques to find the best configuration for your specific problem and data. And finally, monitor the performance of the model during training and validation to ensure that the batch normalization is effectively stabilizing the training process and improving model generalization. Use techniques such as early stopping to prevent overfitting and achieve optimal performance. By incorporating batch normalization into the training process of your neural network, you can effectively improve model generalization and performance, leading to better performance on unseen data and increased robustness to variations in the input distribution. The last thing is the learning rate scheduling that we will talk about in this lecture. So this is a technique that is used to adjust the learning rate during training to improve model generalization and performance. This involves modifying the learning rate over time based on predefined schedules or conditions. And how can you do that? Let's take a look at that in next few slides. So again, choose a learning rate schedule. Select a learning rate schedule or strategy that best suits your problem and model architecture. Common learning rate schedules include fixed schedules, step decay schedule, exponential decay schedules, and adaptive schedules, such as cycle learning rates. Then you implement the chosen learning rate schedule in your training pipeline. If used a fixed schedule, supposing you're using a fixed schedule, set a constant learning rate throughout the training process. If you are using a dynamic schedule, define the function or algorithm to adjust the learning rate based on the predefined conditions or iterations. Then you monitor the performance of the model during training and using validation metrics or separate validation data set. Track matrices such as loss, accuracy, or other relevant evaluation metrics to assess the model's performance over a period of time. Then adjust the learning rate according to the predefined schedule or condition. For fixed schedules, learning rate remains constant throughout training. For dynamic schedules, update the learning rate based on factors such as the current epoch, batch iteration, and model performance on the variation. And then you get on to experimenting with different parameters of the learning rate schedule to find the optimal configuration for your specific problem. Adjust parameters such as initial learning rate, decay rate, step size, or other schedule specific parameters to fine tune the learning rate schedule. Consider using adaptive learning rate schedule such as cyclical learning rate or learning rate warm-up to adaptively adjust the learning rate based on the model's performance and convergence behavior. Adaptive schedules can help improve model convergence and stability by dynamically adjusting the learning rate during the training. Then finally, monitor the convergence of the model during training to ensure that the learning rate schedule is effectively guiding the optimization process. Watch for signs of overfitting or underfitting and adjust the learning rate schedule according to mitigate these issues. Then finally, validate on holdout sets, evaluate the final trained model on a holdout set or test sets to assess the generalized by generalization performance. Ensure that the model's performance on unseen data aligns with the expected expectation based on the validation set. By using learning rate schedule effectively, you can improve model generalization and performance by adapting the learning rate to the dynamics of the optimization process and requirements of the specific problem at hand. So what is next? So we will, having looked at how to iterate the models, and model development process, as well as use techniques that we talked about in this lecture, we will now talk about in the next lecture how to monitor and analyze model training and validation metrics to diagnose any issues and make adjustments accordingly, right? So thank you so much for watching this 13th algorithm selection and development lecture in this course, Master in Artificial Intelligence. I hope you're continuing to learn new things, continuing to enjoy, and I do look forward to see you again in the next lecture. Please feel free to message me if you have any questions. I'll be happy to answer a question, and also download the PDF file to take a look at anything that you need.